Spread out across 200 square feet of dense indoor clover sits a sprawling wooden railway. This massive, multi-level topography is the terrain our Syrian hamster engineer must navigate today. Standard static enclosures often fail to trigger the survival-level foraging behaviors seen in the wild. Without the need to hunt, dig, or scavenge across long distances, these innate instincts can remain dormant. This schematic details our engineering solution. By overlaying a complex wooden track system onto a topographical map of the meadow, we've designed a course that requires cognitive enrichment to navigate. To reach the end, the hamster must negotiate a series of physical and mental hurdles. The journey begins the moment our engineer encounters the locomotive cabin for the first time, picking up the rich scent of grain baked directly into the wood. To encourage movement, we laid out strategic deposits of organic forage along the steepest parts of the track. The scent provide the clear, highly motivating trail guiding the hamster up the initial elevation climb. Replacing a static cage with a dynamic, obstacle-driven layout forces the rodent to work for its transit. We see these natural survival skills engage as the animal begins to navigate. Hitting the first steep incline introduces an immediate physical struggle. The polished track offers low friction, and the train's wheels begin to slip, stalling momentum. To counter the gravity, the hamster learns to adjust its own center of mass. By throwing its body weight forward into the harness, it generates enough force to start the train's momentum against the steep grade. This diagram illustrates the hidden mechanics beneath the incline. A pressure-sensitive pad depresses only when the combined mass of the train and hamster reaches a specific threshold. Once depressed, a mechanical wire pulls a wooden junction gate, setting the route for the descent. Driving this intense physical exertion is a specific payload. Hitched directly behind the engineer are heavy freight cars loaded with raw flax and millet. By successfully hauling that heavy cargo up the multi-level incline, the hamster demonstrates it can use its own body weight as physical leverage to overcome the friction of the climb. At the peak of the climb, the environment shifts. The open track plunges down into the dense clover thickets, where visibility drops significantly. Navigating in the dark requires a rapid pivot. The hamster relies on tactile feedback from its whiskers to trace the walls of the track. This vector profile maps out the concept of dynamic spatial clearance. It measures the maximum geometric expansion of a hamster's cheek pouches against the precise circular diameter of our custom-built wooden tunnels. If we used standard off-the-shelf tube diameters, a hamster fully loaded with grain would wedge itself tightly into the pipe. The custom calculations provide the engineer with enough clearance to pass through while fully packed. Surviving the tight, low-visibility thickets requires a coordination between the animal's natural sensory biology and the precise dimensions of the carpentry. Emerging from the brush, the train arrives at the central sorting yard, a complex hub with multiple intersecting tracks and sharp, sudden turns. Here, the hamster faces a 3-track puzzle. The engineer must choose the correct path, relying on acoustic cues, listening for the rattle of loose grain vibrating inside the correct wooden tube. Taking these sharp sorting turns at speed introduces the risk of derailment. We integrated high-strength magnetic couplings between the cars to keep the heavy train aligned through the tightest bends. When the hamster encounters a blocked junction, it stops to investigate. After diagnosing the blockage, it shifts its weight backward, throwing the entire locomotive into reverse to clear the path. Executing a junction reversal requires distinct spatial logic. The rodent is calculating its pathing and actively manipulating the mechanical layout to move forward. The journey finishes with a final loop through the tallest meadow peaks, bringing the train to the base of the central grain elevator terminal. The engineer unloads the flax and millet cargo, bringing the maiden voyage to a successful close. The behavioral data we collected is mapped on this line graph, which plots the hamster's problem-solving time across successive runs. It shows a steady decrease in the time required to clear the track. This data suggests that when challenged by these environmental hurdles, the hamster develops an efficient internal map of the entire 200-square-foot circuit. The Syrian Express demonstrates the latent problem-solving capabilities of an instinctive forager when it is given a complex environment. With the land routes mapped, the next phase involves custom bridge building and water-based logistics.